Number two, you've got a wiffle ball and a baseball, and we're trying to figure out a few things. Whoops, sorry. Cross-sectional area, maximum height reached, et cetera, et cetera. So they're launched straight up. You've got all this information, and you've got to set up the spreadsheet and then use it to answer some stuff. So let me see if I can get these things showing at one time. The first step here, this says it's both of them are thrown at 30 miles per hour, and they're both thrown directly upward, and they're released from a height of 1.5 meters. So let me take care of that part. On the spreadsheet, initial Y position should be 1.4 meters, and initial time is 0. So this is not like the rocket launch where we're starting this scenario after the thrust phase. So we're starting from time 0. The other stuff, G is always 9.8. I don't foresee anything else. Now this 13.39, I put a little formula in. My formula was 30 divided by 2.24. So that takes 30 miles per hour and converts it to meters per second, which is what you need there. The mass, 0.145, again, I've converted 145 grams to kilograms. So I could do this, equals 145, and they're 1,000 grams per kilogram, so I need to divide by 1,000. 0.145. Air density is 1.27, just like the previous problem. Cross-sectional area, I made a little calculator over here. So this is the diameter in centimeters. And then I put in an equation to divide that by 100, since there are 100 centimeters in a meter. And then I made another super complicated equation to divide that number by 2 to get the radius. And then the cross-sectional area of a sphere is just going to be pi r squared because it's a circle. So this is how you do this one. And the function pi in a spreadsheet is just pi, open the parentheses, close the parentheses, done. So that's 3.1415, etc., times the radius squared. So that's cross-sectional area. Now that I have that set up, I can use that formula for this one and for the wiffle ball. So over here, I just have equals, and then I clicked on this. So I've got a really nice cross-sectional area there. Drag coefficient, we were told, was 0.5. I think that takes care of all of the starting conditions. So now I need to find these things. So the cross-sectional area is just 0.0043008. I don't care how many digits you do, but that would be meters squared. Maximum height reached, according to this, 9.9 meters. 9.9 meters. 9.903, whatever. And if we want that in feet, if we wanted to, I just over here converted to feet. I just put in the formula, the meters divided by 0.305. So that's about 32.5 feet. Time aloft is right there, 2.745. If you do some calculations using 9.8, pretending this is a vacuum, you're going to get a longer time than that, and you'll get a higher height as well because there's drag here. 2.745 seconds. Terminal velocity of this ball is 32.25. It's not going to reach its terminal velocity, I don't think, because it won't fall far enough to do that. In fact, it'll always be approaching it, but it'll get pretty close. The maximum drag force. So this says ignore sign. If you look at drag, it's 0.2449 to begin with, and then it drops down a little bit. And as I go down, if you look in the drag column, column D, it gets smaller and smaller until somewhere around here. It's really small. So that would be the high point where it's hardly moving. And then it gets bigger and bigger and bigger. But these numbers actually look bigger than where I started. But the trick is it's going to hit the ground at some point. So keep an eye on column G. I need to go up until it hits the ground, where the position is 0 meters. All right, right around here, or the time of 2.74-ish seconds. So at that point, the drag is 0.24. And in the beginning, it was 0.244. So it hasn't quite become as strong as it was in the beginning. If it could fall farther, it could maybe, if it landed in a hole, then it could 28 meters below the surface be stronger. But the answer is just 0.24493. That's a tricky one. Newtons. And it's going to be downward. But I said ignore the sign. Still going to put downward. And terminal velocity, really, I should put in negative 32.25. Otherwise, I've given the speed at terminal velocity. Crashdown speed is the speed just before hitting the ground. So I need to go back to time of 2.745 seconds, or a Y position crossing over the barrier from positive to negative here, and look at the speed. So the speed is 13.3 to 13.4. I'm going to say 13.35 meters per second. And since I did say speed, I'm going to leave it positive. Try to be consistent here. Baseball's done. So it goes up, and just for the heck of it, let's convert. I'm just going to mess with this for a second. I'm going to put 13.35 in. Oh no, that's not where I should have done that. Well, let me just do this. So 13.35 and convert that to meters per second, or miles per hour, times 2.24. So 29.9 miles per hour. So it was thrown up at 30 miles per hour and it came down at 29.9 miles per hour. So it's not too affected by drag. All right, now the wiffle ball. So for the wiffle ball, a lot of things are similar or the same, but the mass is different. So I'll do that last because that's the most dramatic thing. The diameter of the wiffle ball is a little bit smaller. So instead of 7.4, it's 7. And my calculator says that the cross-sectional area, therefore, is 0.0038485 meters squared. Meters squared. And the maximum height reached was, oh no, I'm not done. Not done. Need to put in the mass. 19 grams. So here, instead of 145 divided by 1,000, it's going to be 19 divided by 1,000. All right, so that changes things quite a bit. Zoom out over here. I'm just checking to see if I have everything. So 1.4 meters is the release point, 0 is the starting time. We're assuming a drag coefficient of 0.5, cross-sectional area, density, mass, velocity. Yep, so this is all good. All right, so the maximum height reached is 7.48 meters. So 2 meters shorter. And the time aloft is 2.375 seconds. So it doesn't stay in the air as long as the baseball. Terminal velocity is 12.3 meters per second. But I'm going to put negative because that's downward. I'm getting that from right up here. Maximum drag force. Again, I can do the same kind of thing I did before. Look at the drag at the beginning. It's 0.219. And then I can go until it hits the ground, which is going to be at 2.375 seconds. So right around here. Rows 246, 247, and the drag force is only 0.11. So it's a much smaller one. So it's definitely the strongest drag right in the beginning. And that's because it's falling so slowly by that point. So the maximum drag force is 0.2192 newtons. And I'll call it negative because it's downward, even though I say ignore the sign. What I meant was ignore the sign for finding when it's the strongest. Find the one with the highest absolute value. And then crash down speed. Again, I need to go to when the Y position is 0 at 2.375 seconds. Right in here. And then I need to look at the Y velocity. The Y velocity is negative 9.7. But I'm going to put 9.7. All right, so it's not going very fast, and that's it. I think this might have been more interesting if we had made this a lot faster. If I put in a much faster velocity, then you would see much bigger differences between these two. If I had this to do over again, I would make it less realistic. I was thinking 30 miles per hour. You're trying to throw straight up. It's hard to throw straight up very fast, but if we had done this at 100 miles per hour, baseball would have gone way farther and stayed in the air way more time. And the wiffle ball would have been much slower when it hit the ground.